is your video for 5.2 on the mean value theorem. This is our second section in chapter 5, and the first three sections, as I already stated, are all about finding things out about a function based on what's happening in the first derivative and what's happening in the second derivative. So this is theorem 3, and I will scroll a little bit because I know this video is kind of in the way of being able to see some of that. This is your mean value theorem for derivatives. You do have to state that it is for derivatives because there's also a mean value theorem for, and I'm blanking on the name here, mean value theorem for antiderivatives, which are for integrals that we will be using when we get to chapter 6 and 7. So you have, if y is equal to f of x is continuous at every point in the closed interval, in the closed interval, differentiable at every point of the open interval, then there has to be at least one point C in your interval a to b where the derivative at c is equal to f of b minus f of a all over b minus a. So that means if you take any point c, which is in between a and b, and you take the derivative at that point, that's your instant slope. There has, or I guess rather, you're not really picking the c here. You have your a to b interval. The average slope, that secant from a to b, there has to be at least one place where the derivative is equal to what that instant slope is. And I have a drawing here for that. So if I have this red function here, and I have my a and I have my b, and I draw those, and I draw in the secant line from a to b, there has to be, because this is continuous and differentiable on the open interval, there has to be a c, which I drew in here, where the derivative at c, the slope at c, is the same as the slope from b to a, or a to b. Notice I did draw, those two lines are parallel because they have the parallel markings. This part here that is cut off, let's see here, let me extend that a little bit so you can see that. It says somewhere between points A and B on your differentiable curve, there is at least one tangent line that's parallel to chord AB. There could be multiple tangent lines, but there does have to be at least one place where that tangent is equal to the average slope from A to B. Okay, still at the top, this is an existence theorem. So it tells us that something has to happen, but it doesn't actually tell us how to find it. But this example, this first example we're going to use here, we're going to show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem, or hypotheses, on the interval 0 to 2, and then we're going to find the solution to the equation. So you're actually going to figure out how to use the mean value theorem here. Well, first of all, to satisfy this, f of x is equal to x squared. Change to a different pen here. This is continuous on 0 to 2. It's polynomial. All polynomials are continuous. And it is differentiable on the open interval 0 to 2. So because it is continuous and differentiable, it does satisfy the mean value theorem. And there are some questions on your homework where all it's asking you is, does this satisfy? This does in fact satisfy here. So now we want to take the derivative. And then I also need to find the average slope from 0 to 2. So f of 2 is 4. F of 0 is 0, and then I'm going to set these equal. You can use c in place of x if you would like to. You don't have to, though. You can just use the x if you want to, but I know they use c as the value there. So my 2x is equal to 4 minus 0 over 2 minus 0, so you subtract the y, subtract the x's. So 2x is equal to 2, x is equal to 1. So 1, the slope of 1 is going to be the same value as the average slope from 0 to 2. So 1 is where this would satisfy the mean value theorem. Page 203 has an example. I want you to just read over that. You can probably watch the video that goes along with the book to get that information as well, because I'm pretty sure that they go over that too. Then we have example 3. So we're going to let f of x equal the square root of 1 minus x squared. Your A point is -1. Your B point is +1. Notice this says f of -1, f of 1. That would be the y coordinate. We want to find a tangent to f in this interval that is parallel to secant AB. So from A to B, we want to check this graph is in fact continuous on -1 to 1, and it is differentiable on the open interval -1 to 1. So it would satisfy the mean value theorem. There are places where this does not exist, where you wouldn't be able to take the derivative, but in the intervals that are given, it's okay. So we have our f prime is going to be 1/2 1 minus x squared to the -1/2 power times -2x. So cleaned up, that's going to be -x over 1 minus x squared to the 1/2 power. My average slope from A to B, so I'm going to set this equal to f of 1 minus f of -1. Well, if I plug in 1 here, I'm going to get 0. If I plug in -1, I'm going to get 0. So I have 0 minus 0 over 1 minus -1, which is going to be 2. This is just 0. So to find the place where this satisfies, where this fraction is equal to 0, I want to set the -x equal to 0. And that means at x equals 0, that is going to give you the same slope as A to B. Now we need to find, it does say find a tangent. That means find the tangent line. So I have 0 times x minus, I can go ahead and use the second point, x minus 1. And then blank in there. Y value is, at 0, sorry. That's not going to be it. 0, if I plug in, because my point here is 0, 1, that's going to be the value that I'm using. So 0 times x minus 0 and then plus 1. I don't want to use A and B because that's not where I'm drawing my tangent line. I'm drawing my tangent line at x equals 0. Slope is 0, so that means your equation is y equals 1. If any of these, if you have any questions on them, please reach out to me. Don't just sit there and stew on whatever questions you have. If you need something cleared up, please make sure you ask. So this example, it's actually already worked out. There is a picture in your book on page 204 for this. And this is probably one of the best ways to demonstrate what the mean value theorem is. It is related to the extreme value theorem, intermediate value theorem, which tells us that we have to have proof that something crosses the x-axis if it's continuous, and at one value it's negative and another value is positive because it can't just jump. This is kind of related to that. So you have a car accelerating from 0, takes 8 seconds to go 352 feet. Its average velocity for the 8-second interval is 44 feet per second, or that's 30 miles per hour. So that means no matter how fast the car ends up going, at some point during the acceleration, your mean value theorem states that your speedometer has to read exactly 30 miles per hour. You can't have an average without reaching that point at least at some point in your trip. So for example, if you're starting from 0 and you end up at 50 miles per hour, your average rate of change would be 50. So that well, I guess it depends on how long that you take to do that. But like for this one, 352 divided by 8, 30 is your average. So even if you end up going 40 or 50, there was some place where your speed had to be 30 miles per hour. And that's what the mean value theorem says. Whatever the average rate was, so for example, here's a better one. If you get up to 50 miles per hour in 5 seconds, there had to be at least some point where you were going 10 miles per hour because 50 divided by 5 is 10. And that's the mean value theorem. It only works if your function is continuous on the closed interval, differentiable at the open interval, and speeds in a car are going to be continuous because your car can't jump miraculously from one speed to another without first hitting everything in between. Okay, so now we're going to look at some other key pieces of information that go along with derivatives and first derivatives and what we can tell. This is kind of an algebra review. So if you have a function defined on an interval I, x1 and x2 are any 2 points in I, we define your function as increasing if x1 is less than x2 and f of x1 is less than f of x2. So basically the lower x gives you the lower y. That means that a function is increasing. This is not calculus, this would be an algebra type problem. It would be decreasing if your x1 is less than your x2, but your f of x1 is greater than your f of x2. So that means the lower x gives the greater y. That would be decreasing. So again, this is algebra definitions. That brings us into this corollary, which is where we get into the calculus. So they had to define increasing and decreasing as far as algebra goes so that we can make the connection to derivatives. So you have to let f be some continuous function on a to b, and it's differentiable on the open interval a to b, if your first derivative is greater than 0. Well, again, greater than 0 means positive. So if your first derivative is positive at every point in your open interval a to b, then your function is increasing on a to b. If f prime is negative, so less than 0 at each point of a to b, then your function is going to decrease. So this we've already been talking about. So we have the corollary now, but we've been looking at this with graphs because we said, well, if you look at the graph of the derivative and it's in the negatives, that means the original function has to be decreasing. That's all this is saying. If your first derivative is in the positive area, that means the original function was increasing. So this is another one of those non-examples in that it's an example, but it's already worked out. So if you have that function again, y equals x squared, remember that's going to be your parabola that comes down and then goes back up. It is decreasing from negative infinity to 0 because y prime is 2x, and if this is my 0 here, if I plug in any value on this interval into the derivative, I'm going to get a negative value. It's increasing from 0 to infinity because, again, y prime is equal to 2x, and that 2x is always going to be positive if I plug in anything from 0 to infinity. Sometimes it's a good idea to create a chart to kind of keep track of where the first derivative is positive or negative. And this example 6 is the first place where you're actually going to see that. Just one thing to be aware of, they do not accept charts alone as justification on the AP exam. You can use a chart or a line grid to organize your thoughts, but then you have to state, this is happening here because of this. So basically, as long as you go back and restate with a sentence what's happening in the chart, then it's acceptable. And we'll talk about that more when we get closer to AP exam time. So we want to know, where's the function increasing, where's the decreasing? We're going to use calculus. The first thing you need to do is take the derivative. So my derivative here is 3x squared minus 4. We want to see where this is equal to 0 because 0 is going to be your boundary between the positives and negatives. And then we can look in between those boundaries, see what sign our first derivative is. I can solve this using the square root property. So x squared is 4/3. Take your square root. And x is equal to plus and minus 2 over the square root of 3. So now I'm going to set up a number line to figure out what's going on here. So there's negative 2 over the square root of 3 and 2 over the square root of 3. And I want to know what the sign, does not look like the word sign of y prime. So I'm going to pick some values that are in between these, and I'm going to plug them into the derivative and figure out what the sign of the first derivative is. Now, in between them is 0. You don't have to know exactly what the value is as long as you pick something that's definitely greater or definitely less. So for example, I know that 5 is going to be greater than the greater one, and negative 5 is going to be less than the lower one. So I'm going to take all of these and plug them in, and I'm going to see if I get a positive or negative value in the derivative, which is here. So if I plug in negative 5 here, 3 times negative 5 squared minus 4, I don't need to know the exact value, but I do know that that is positive. That's definitely going to give me a positive value, which means y is going to be increasing there. Let's separate those out. So the sign of y prime is positive, which means y has to be increasing. If I plug in 0, 3 times 0 squared minus 4, that gives me a negative value. Again, I don't need to know exactly what negative value, I just need to know that it's negative. And since it's negative, that means that y is going to be decreasing. Plug in the 5. 3 times 5 squared minus 4, well, that's definitely going to be a positive number. And again, that means that my y value is increasing. So then to state our final answer, because this says where is it increasing, where is it decreasing, we can't just leave the chart as our answer. We actually have to state it is increasing from negative infinity to negative 2 over the square root of 3, and from 2 over the square root of 3 to infinity. If this was on the AP exam, you would have to say because y prime is positive on the intervals. And then for decreasing, that is decreasing from negative 2 over the square root of 3 to 2 over the square root of 3 because y prime is negative on the interval. If you can't read any of my handwriting there, just reach out to me, or you can look at the PDF. It's a little bit easier to read in the PDF that we have for this. So this is really the first bit where we are taking a look at the derivatives and seeing, just based on the algebra and not a graph, what has to be happening in the original function. In part 2 of this section, we are going to look at working backwards from derivatives to the original equations, and a few other theorems and corollaries that go along with this. So go back, rewatch the video, and reach out to me if you have any questions.